Hi everyone, today we'll be discussing Thevenin equivalence and source transformation, and we'll get started with that. We've gone over the overview before, so I'll start with source transformation. So basically, when we're talking about source transformation, we're talking about voltage sources and current sources. If it's beneficial, we could convert a voltage source into a current source in a circuit, and vice versa. This can be useful at times where we can simplify the overall circuit by transforming, for example, a voltage source to a current source, or transforming a current source to a voltage source. And the idea behind this is based on the equivalence between these two sources. So let's start. A source transformation would look, as you can see at the bottom of this slide. What we will have is a voltage source that has a resistance in series with it. We could replace that with a current source that has a resistance in parallel with it. It's important to try to determine what should be the values of these new source transformations. So for example, if you have a Vs and R is obviously going to stay constant, it's not going to change, but how do you actually adjust the Vs? How does that transform into this Is? And we'll look into that in the next slide. So the idea here is that if we go back, the overall voltage at these two terminals is given by Vs is equal to Is times R. So Is times R, the current that is flowing through that terminal, is equal to the voltage. So if we redraw the circuit, what we can say is now, with the current source, that the Is should be equal to Vs divided by R. So if you transform the voltage source that has a resistance R in series with it to a current source that has a resistance R in parallel with it, the new current source value should be Vs divided by R. And vice versa, if you have a current source that has a resistance R in parallel with it and you want to transform that into a voltage source, the voltage for that source transformation would be Is times R. Now, what happens if we're dealing with dependent sources? Well, nothing really changes. We keep everything almost the same. So we could also transform dependent sources, and this can be very helpful, again, in solving circuits. And the relationships that hold between dependent sources are identical to independent sources. So if this Vs, for example, which is dependent, corresponds to some Vs in the circuit, when you transform it to Is, well, you divide that Vs by R to arrive at the new Is. So whatever that voltage that you're dependent on, you divide it by R, and that's a new source transformation. It is important to remember that the direction when you go from a voltage source to a current source, the direction of the current or the arrow for the voltage source should be pointing from the negative to the positive that corresponds to the voltage source. Although source transformation is not possible if we are dealing with ideal scenarios, but remember that we could have resistors that are in series with ideal voltage sources. We could have resistors that are in series, that are in parallel with ideal current sources. So we can still apply this in the circuit. However, in reality, I guess if you wanted to just do a source transformation, you couldn't do it with ideal sources. We'll solve some problems in class about this. But what this leads to is the concept of Thevenin's theorem, which is a very powerful theorem, and we'll discuss why. But basically, the issue is that we a lot of times have these variable parameters that are within a circuit. Yes, I know in the circuits that we solve within the course, a lot of times we're looking at fixed values for resistances and fixed values for the for many other parameters when we're trying to find the voltages and currents within the circuit. However, in reality, what we have is this variable element that gets connected to the circuit, and that's usually referred to as a load. So for example, if you look at the outlet, you connect all sorts of different devices to it. You could have a heater, light bulb, iron, whatever. The point is that you're connecting different things, and those different things have different voltages and different resistances, which could affect your circuit differently. So the challenge is that every time you change the load, you have to reanalyze the whole circuit to see how it behaves, and sometimes that can become very complex. So the idea is that if we could represent all the constant parts or elements within the circuit by a black box with two terminals sticking out of it. And then we could represent the load as something that changes its resistance, then it would be much easier to analyze the circuit, because what we would have is that we would have this two-terminal device, and then we would just connect the different loads to it, and we could easily determine the voltages and currents that are flowing within the load. So Thevenin's theorem mentions that what we could do is replace all excuse me, all the elements with a voltage source with a resistance that is in parallel with it. So all the constant elements that are changing can be replaced with a voltage source and a resistance in series with it. Now the voltage of the voltage source is the Thevenin voltage, and the resistance that is in series with it is the Thevenin resistance. So we have to determine those, right? So we have to determine. Now the resistance is determined by turning off all the independent sources within the constant circuit, and then determining its resistance and putting it there. And the voltage is determined by just determining the voltage across the open terminals of, again, the constant circuit. So this can be very helpful, because now when you connect these different loads to this circuit, it's so easy to try to determine what is the current flowing through the load, what is the voltage that you're supplying to the load, and it doesn't matter what load it is, as long as you have the Thevenin equivalent, it would be so easy to proceed from there. As I mentioned, when you're trying to find the equivalent resistance, there are two set of cases. Case one is that you don't have any sort of dependent sources. So you find the resistance by just simply turning off all the sources. And we've done this before when we were looking at superposition, remember? So we're using superposition again here. But we did this before in superposition. So when you're turning off sources, when you turn off a voltage source, you basically just replace it with a short. And when you turn off a current source, you replace it with an open circuit. So that's what you would do. And then you look at the equivalent resistance of the circuit when you're looking into it. Case two is the scenario where you do have dependent sources. And this case is not as straightforward. You still turn off all the independent sources, as we mentioned before. However, it's not easy to find the actual equivalent resistance. So what you have to do is apply a test voltage and then try to find what I0 is. You could apply a test current and find what V0 is. And then from there, you would basically use Ohm's law as R Thevenin is equal to V0 divided by I0, or R Thevenin is equal to, again, V0 divided by I0 to try to find your answer. So you know what V0 is, you just need to find I0, and then you would find R Thevenin. And here in this case, you know what I0 is, you just need to find V0 to again find R Thevenin. And the reason you need to do this is because you have these dependent sources that are basically dependent, and the voltage that they generated depends on different parameters, and so you have to apply the test voltage. So as I mentioned before, it's a very powerful theorem because it simplifies the overall structure of the circuit into just a voltage source and a series resistance, and then you can easily analyze the circuit when you connect different loads to the circuit. Now, you could have a large circuit that can be replaced by, a single source and a single independent resistor, so that's again very helpful. The behavior of the circuit, what is beautiful, is that it's the same as the original circuit, the complex circuit you had, so that's very helpful. It is important to mention, though, that when you have dependent sources, excuse me, and you're trying to find the equivalent resistance, you could actually end up with negative values of resistance. And what that means is that the circuit is actually supplying power with all the independent sources still turned off. So that's fine. I mean, that's a possibility and that could happen. So, but do not feel like you could not end up with that. So the negative resistance means that you're supplying voltage. And as I mentioned before, it would be much easier to try to determine what happens with the overall circuit when you connect the load. With that said, we will solve some more problems in class and clarify the topics better.